let me turn off this here. Not so necessary. Okay. Okay. We are at B trees. We are going to talk about B trees today first, and we are going to continue with skip list. Maybe one. B tree is generalization of this 2-3 tree structure. In 2-3-3, each node may have 2 or 3 children, but in this B tree, we generalize it, and each node can have as much as n children. Okay, it's a generalization. It may have more values. Each node can store more values and more children in turn. Okay, these B-tree structure usually used to store databases on hard disks in secondary storage. So B-trees are not for in-memory operations usually. It is more used on secondary storage operations. Remember, if the values needs to be stored permanently, we store them in hard disks, and for that, still we need to access the values fast. We may need to perform search operations, insertions, and deletions. So to be able to perform these operations on secondary disk, we need some structure to perform these operations fast. B-tree is one of them. So it is not a in-memory data structure. It is secondary storage data structure, but still it is the generalization of 2-3-3. So we would like to talk about these B-tree structures. The data structures we have seen so far are all in-memory data structures to store the data in the memory, but this B-tree structure is secondary storage data structure. As I said, it is used to store very large databases on hard disks. Okay, we are not going to talk about this 2-3-4-3, but it is also a special case of B-tree, and you can look at it in the book. It is available in the book, but I'm not going to talk about that tree structure. This is how B-tree is formed. As you see, each node in the B-tree can store more than one element, so it is not a binary tree, and it may store a lot of elements, and in turn the elements less than 10, less than the smallest value, is the leftmost child, and elements larger than the largest value in the node are stored in the rightmost child. And of course, in between these two, we have many more elements. So in elements between 10 and 22 will be stored in this child, etc. So this tree structure has 5 children. This 5 is the order. It's called order of the B-tree. So we are going to talk about one order value for each B-trees. That is the number of children for a node, which is the maximum number of children. Since sometimes, for example, for this node, if there are children, we may have 3 children only. In this case, we may have 4 children, and 5 is the maximum. So this value is the order of the tree. The order value would be any value. In this case, it is 5. When the order is 5, each node stores 4 values, one less than the order, right? At maximum 4 values. And this number of values stored would be as little as half of the order, not less than that, except the root node. Root nodes may have 1 or 2 or 3, whatever values, number of values, but the other nodes should store at least order over 2 values. We are going to talk about it in a minute in detail. Okay, so the maximum number of children is called order, and this order value is 5 for this tree. Number of data items is 1 less than this order value, 4 in this tree. And each node, other than the root node, as I said, may have any number of children. In this case, it has 5 children, but it's not necessary. It may even have 2 children. But the other nodes, other than the root node, number of children should be between order over 2 to order. Order is the maximum, and order over 2 is the minimum number of elements. If the number of children is less than order over 2, we have to perform some operations to fix this problem. Okay, and if the number of children is more than order, again we have to fix this problem somehow. So the number of children is in between these 2 values. We keep the elements in each node in increasing order. So the values less than 10, which is the minimum element, will be the leftmost child, stored in the leftmost child. The first link from a node contains the elements smaller than the minimum value, and the rightmost link from a node connects to subtree. We may have a subtree here, and all the values in that subtree is greater than the maximum value of 40. Okay, and we have intermediate links. We have 3 more links here. The first intermediate link is the elements between it has a subtree element which contains elements between 10 or 22, and of course this link is 22 and 30, etc., etc. Okay. So as I said, B trees are used to store databases in secondary storage. Actually, we store indices of the database. Indices usually have 2 values, index value and address value for the this is key, index is the key, and the value is the address of this entry in the database, in the secondary disk, of course. So by using this thing, we can locate the entry in the secondary storage. So we use to store keys or indices in secondary storage, of course, and in secondary storage usually structured as blocks. These blocks is large blocks, like couple of megabytes probably. So each block may keep lots of indices, not only one. So the running time of this access, the running time of the operations usually depend on the number of block accesses, since the block access is the most time-consuming operation in databases. So we would like to minimize the number of block accesses. So when you access a block, you would like to use that block as much as possible. And in B-tree, each block keeps one node in the B-tree. So each B-tree has enough lanes and values to fit in a block and completely use that block. Okay, so the order value is designed so that the whole block is used for that node in the B-tree. So when you access that B-tree node or that block, you use the whole values, the whole block, and try to locate the next B-tree node. Okay, so each disk access retrieves a B-tree node, and we look at that B-tree node to find the next children of that B-tree node and continue like that to access the real value, the database entry. So the running time, as I said, depends on the number of block accesses. So by making a B-tree node to fit in a block, we can reduce the number of B-tree nodes accessed, or in turn number of blocks that needs to be accessed. Okay, this is why retrieving a block from disk is quite larger than the processing time of that values in the memory. You access the block, get it into the memory, right, and process that values, that node in the memory, right? And processing in the memory, processing that node in the memory is a lot faster than getting that block from secondary storage to the memory. So we would like to keep the number of block accesses as little as possible to make our database access faster. Okay, by making tree nodes as large as possible, as large as a block, we reduce the number of disk accesses and in turn the running time of the operation. Running time of the operation to find an index value for an item to research. For example, we assume that each node has an order of 200. So we can store 200 children for that node. Means that is the maximum, right? Maximum 200 nodes. And the minimum is 200 over 2, which is 100 children, right? If we have 100 children, the number of values is one less. It is quite similar to 100, and we can assume that the number of elements, the least number of elements in a node is 100 as well. In that case, if we have a database with 10 million items, that is 100 to the 4, we can find the elements, search element, with 4 B-tree node access, right? Since the height of the tree, if height of the tree is 4, and the number of child is 100, then 100 to the 4 elements can be stored in the tree. 100 to the 4 is 100 million. 100 million elements can be stored in this tree. That is the minimum. The maximum is, of course, 200 to the 4. If there are 200 children for each node, we take the minimum number of children in this case, and for this many elements, this is quite a large value. As you see, if we keep the index value for each person in this country, in Turkey, the number of people is less than 100 million. So we need only 4 disk accesses, or 4 node accesses, or 4 block accesses to be able to search any value, any person in our database, right? And this 4 is quite small, and it makes the running time faster, okay? That is why we use B-trees for secondary storage. Okay? Now we are going to talk about how to perform insertion and deletion operations. Actually, search is simple. We start from the root. We search the value here in the values in the root, and try to locate whether the search element is available at the root or not. If it is not, if it is between 22 and 30, we follow this link and get to child and search at this subtree recursively, right? So the search operation is simple. At each node, we have a constant number of elements, so each node can be considered as constant, and the height is logarithmic to base 100, of course. That's why it is quite short tree, but still the running time is logarithmic. Okay. What about insertion and deletion? Insertion and deletion operations are similar to 233, since it is a generalization of 233. Similar to 233, the insertions are performed on the leaves. For example, we can insert the values less than 10 in this leaf, and values between 10 and 22 in this leaf, etc. Okay. If we have to insert 39, 39 is in between 30 and 40, so it is not in the root, so we have to insert it. We follow this link to find the next node, and until a leaf. When we find a leaf that doesn't contain 39, we insert it in proper place in this sorted. This is a sorted list, right? Sorted array. So 39 is inserted in here in proper place. Since it is greater than all the values, it's going to be inserted here, right? Okay. But if the leaf is full, it doesn't have more empty space to keep a new element, we have to split the node as in 2, 3, 3. Remember, if we have 3 nodes and we have to insert in that node, we split the 3 node, right? Similarly, we perform the same kind of operation. We split the node into 2 approximately equal size, half size nodes, and the middle element is passed to the parent to be inserted at the parent. We call it new parent and inserted into the new the parent node. For example, here if the parent is full, of course, it has to be split again, and the middle item will pass to the parent, etc., until the root node, of course. If we have to insert 17 in this tree, 17 is between 10 and 22, and it's not on the root, so we perform insertion on this subtree, and we follow the links until the leaf node. We have the leaf node directly, and in this leaf node we have to insert 17. 17 will be inserted in between 15 and 18, of course, but since this node is full, we cannot insert and complete the operation. It requires a split operation, right? So when we insert 17, actually we cannot make this, since this is larger, the number of values is 5, it is not possible, so it cannot be inserted. But what we have to do is to split these 5 nodes into two nodes, and 17 will pass to the parent to be inserted, right? So we form 2 nodes, and 17 is passed to the parent to be inserted. Of course, parent has 4 elements already. Inserting 17 in this place is not possible, since it is full. It has 4 elements already, so we have to split the parent as well. So 17, insertion of 17 is not possible, so we split it into 2. One will contain 10 and 17, another one contain 30 and 40. 22 will be passed to the parent. Since there is no parent, we will create a parent node which will contain only 22. As you see, the parent contains only 22. Remember, each node can contain, the order is 5. 5 over 2 is 2. So we may, actually, we should be 2.5. The number of children should be greater than that. So we take the ceiling, which is 3. So the number of children could be 3, 4, or 5. But in this case, the root node has 2 children, and that is possible for the root node only. Root node may have less than this many children. Okay, order of root 2. Okay, this is how we perform insertion. As I said, insertion is performed at the leaves, and after the insertion, if the leaf is full, we should split. For example, after adding 28 and 29, and if we add 25 as well, it should be inserted here, right? But it doesn't have enough space, so we have to split into 2 nodes, and 27 should be moved to the parent. So parent will have 27, 30, and 40, right? And it will continue like that. Okay. So to be able to implement B-tree, we have to define a node structure. In this node structure, it's a inner class of B-tree class, right? We keep a size, a number of data items in the node. And we need an array to keep the data, and we need an array to keep the references to children nodes. Okay. So we have 3 data fields. The values are stored in an array, and these references are stored in another array. Then we have to create a node. This is the constructor. We have to specify the order as a parameter. The order is not stored in this node structure. The order value is stored in the B-tree class, and it is fixed for the whole B-tree instance, and for all the nodes in that B-tree, it is fixed value. It is this invariant is made sure by calling this constructor with the same order value for all the nodes in the same B-tree actually. And the number of data elements will be 1 less than that order value. And that values should be comparable. Since the comparables are casted to this generic class, we may have warning. That's why we need to have this suppress warning signal. Okay. And of course, we have to create this many childlings, right? So we create an array of nodes this many order of nodes, right? And size is 0 at the beginning, and it will be, when we insert new nodes, it will be changed properly. So this is an internal class for B-tree class. B-tree class is a generic class. The values in that class and that structure should be comparable. Okay, and in B-tree we keep a root node, and the order, as you see, order is an integer, and the constructor is simple, that sets the order, and empty node is empty tree is created by making root to be null. Okay, this is the insertion algorithm. In insertion algorithm, we have two special cases. One special case is if the tree is empty. If the tree is empty, it doesn't contain the item, of course. And since tree is empty, we create a one node tree, which is the root node, containing that element, one element, and return. Another special case is when the search item is at the root. If we can find the element at the root, if the item is in the local root, then we return false, of course, since we cannot insert the same item again and again in the same tree. And the rest is the general case. Here we have the case of the local root is leaf. We start from the root actually. We search the element in this root. If we can find it, we return false, of course. If we cannot find it, we say that the value has to be inserted in between these two values, in turn in a child of it, right? A respective child of it. And we perform a recursive call here. So if it is not root, we perform a recursive call. But if it is not root, it means this node is a leaf node. What we do is we find the place to insert. We have to insert in this place. And if the local root is not full, we just insert in this place and we are done, actually. Insert a new item and we are done. How do we say we are done? We make the new child to be null. We are gonna see that we may need to return a new child and new parent to the parent to be inserted at the parent. We are gonna see that new child is null, and we return true for successful insertion. Otherwise, if the local root is full, we cannot insert the value in between these two. What we have to do is to split this node around this middle element. These are the values to be in the left child. These are the values to be at the right child. and we move this parent to this middle element to the parent. So we split the local root into two. So this will stay in this value, but we will create a new node and copy everything here to this one. And this is a new child. And this will be the new parent. We move new parent and new child to the parent to be inserted at the parent. So in this case, after split operation, we will have a new parent and new child, and we return these true value besides true, which indicates successful insertion. Okay. Of course, when we perform a recursive call, if the root is not a leaf, we have to perform a recursive call for proper child. For example, we were here in this node, and we decided that this child has to be called. We perform insertion in this place, insertion in this subtree, and we may get a new child and new parent as return value, right? So we have to handle this new child and new parent. Here we handle them. If the return value of new child is not null, so there is a new child and new parents, we have to insert new child and new parent in between these two. Of course, there are two cases, as in leaf. If the local root is not full, we insert new parent into data array, new child into the child array, and make new child to be false, new child to be null, and return true for successful insertion. So it will not, this new child and new parent will not propagate to the parent node. But if the local root is not full, means if it is full, then we have to split this node as well around middle. This part and this part will be stored in two nodes. Actually, a new node will be created, and this will be copied, and this new parent and new child will be returned as well to the parent, as in here. Right? And we return true to indicate successful insertion again. If the new child is null, else, we perform the successful insertion. Also, we return true or false information that we receive from the recursive call. This is how we perform insertion. As you remember, we use helper method to perform insertion in binary search tree and all these AVL tree, etc., etc. We use helper method that performs the operation recursively. The regular method is used that helper method. The regular method is not recursive and gets the item only. There is a method insert which is public method which takes the item only, and that method will perform this operation. This special case is handled by the public insert method, and if the root is not null, the helper method is called. This is a recursive helper method which uses the root node and the value to be inserted as a parameter. The first thing to do is the search operation here, right? Search the local root for the item. So we can perform it by using binary search, since the values at the local root are stored in sorted order from smallest to largest. We can use binary search. We use binary search, perform binary search on this array, and we search for item, and from this index to this index, this is the size, the number of data pieces, right? We perform binary search and we get an index value. If the element is not in the array, data array, we get the position of the first largest array, largest value. So if it has to be in between these two, we get this one, right? So if it is larger than all the values available here, we give an out of size value. If the index is root size, we know that the element is not in the array. And if this value is not equal to the data we are searching for, then it is not in the array, right? Otherwise, if the index is if the value is equal to 0, we found the data. If we find the data, we have to return false, right? If we couldn't find the data, we have to perform insertion. And insertion is implemented as in here. As you see, if the index value, in the child as index value is null, which means we are at a leaf, since if the child here is null, means there is no child here, and if there is no child here, there is no child here, there is no child here, that this node is a leaf node. If it is leaf node and the order, the size is less than order -1, means it's not full. We insert the item in that index place, right? And we make new child to be null. Otherwise, we have to split. Again, if the we have to perform a recursive call to insert if the node is not leaf, we have to make a recursive call to this child, right? We checked it is not null, right? Already. So we make a call to insert, and after this call, we get a result value, which is a Boolean value, true or false, successful or not. Besides, we get two more pieces of information, new child and new parent. This new child and new parent are data fields that is here. That needs to be defined here. It's not shown, but there are two more data fields that are used as a return value of insertion. Okay, and if the new child is not null, we have to insert that new child and new parent at that node. As you see, new parent is the value to be inserted, and new child is the child. For example, if we have to insert in between these two, here, there is a child here, there is a child here, right? This child stays like it is, but this is a new child. A new child has to be added as well, right? So this new child is provided by this insert operation, and we insert this new parent into data array and new child into child array in this insert into node method. Remember, this node has two pieces of information: child array, data array. New parent is inserted in data array. New child is inserted in the child array in index position. If the child is, excuse me, if the size is equal to order -1, means it's full, then we have to split. As you see, we pass new child and new parent to this split operation, as in here, the item, and null is for the new child in this leaf case. And we have to insert in this position at this node, right? After split operation, new child and new parent values needs to be modified during split operation. Split node method, new parent and new child has to be modified so that it is passed to the parent up to recursion one more level. Okay. This insert node is simple, of course, to be able to insert in this between these two. Everything here should be moved one position to the right. This is done here. Node size to index by subtracting. We move everything, both the data and child array, one position to the left. Remember, we have two arrays, child array and data array, both. We open up a position for the new data here and insert this new data. Both object, new parent, and new child are inserted in its places, and size is incremented, of course. Okay. We have to be careful. Data has to be inserted in index position, but the child has to be in the next position, since for each data we have, before the first one, we have a child, and this is the place for this one, this is the place, etc. So one more child is available as a first child. Split operation is figured here. Actually, this is the full data value. This is the place tree. This is the middle one. Based on middle one, this data value is modified as this one, but a new node is created as well. Everything here is moved in this place, and we have another value either to insert here or insert here, right? And this new parent and new child will be passed to the parent. This is the algorithm. You have to be carefully review this algorithm, this code. It is not too complicated, but you have to be careful. First, we create a new child here for this one. This is a new child. This is the new child that we split off node, new child, and we calculate the number of elements to move to this new child. Half of the values will be kept here, and the rest in this place will be moved into this new child. So we calculate that one. And if the insertion position is in here, we move one place to the left. So the number of moves is decremented. Okay. And the elements until non-move will be copied into the node to new child for data and for the child array. So for the child and data array, the values in node will be copied new child that we created here. So for data, these are copied here. For the child array, we perform the same operation and make the copy. Of course, this the node size of this node and size of this node has to be set properly here. Okay, sizes are set, and of course we have a new node needs to be a new node and new parent to be inserted either here or here, right? There is one more special case. It will be in the middle as well. This value would be the middle element. If it was the middle element, new parent and new child is the item and the child value. Otherwise, we insert the item and child to the node, or item and child to the new child. The places to insert would be you should be careful about that, but you can easily do it. Verify the values. You insert this value into this array or into this array here. Then the middle element is set to be new parent. This is the middle element, set to be new parent, and new child is the child of the middle element. So the child here is the new child actually. So node size is decremented afterwards. And as you see, this one, right? So the value here and here are still over here, right? We have to make them null to make sure that the garbage collector will collect when they are deleted. If they still here, we still have reference to the items, even if they are deleted. Since we have the references, we cannot, a garbage collector cannot reclaim the memory space reserved for that items. So we have to make the data fields and child fields to be null for this place. This place is null since we have created this from scratch, but here this place has to be made to be null in the node structure. Okay, this is generalization of the insertion in the 222 actually. Before we talk about the removal process, let's have a break of 10 minutes. It is 10:35 now. Until we are gonna have a break until 10:45. Okay, we are gonna have a break until 10:45.
See you in 10 minutes.